In this video, we are going to analyze boost converter. The boost converter is another switching converter that can make output voltage larger than the input. We follow the same procedure as buck converter. We start examining the inductor voltage and current for the switch on and off. When the switch is on, the equivalent circuit looks like this. The voltage on the inductor is Vin. So let's put the Vin on the voltage waveform of VL. Then we know that the voltage on the inductor is di on dt equals to Vin divided on L. After rearranging, we can get the relationship between current ripple and inductor, which is delta IL divided on dt equals to Vin divided on L. When the switch is open, the inductor current cannot change instantaneously, so the diode is forward biased to provide a path to inductor current. In this case, the voltage on the inductor is Vin minus Vout. And we also know the voltage relationship, the voltage-current relationship on inductor is VL equals to L di dt. After rearranging, the change in inductor current is computed. Again, the rate of change of voltage is constant, so the current increases linearly. For the steady-state operation, the net change in inductor current must be zero. So, the same as bus converter, the current change on stage plus current change on off stage on inductor is zero. Then we find the relationship between input voltage and output voltage is Vout equals to Vin divided on 1 minus D. Then also we want to know the maximum and minimum inductor current. To find the maximum and minimum inductor current, we firstly need to know the average current on inductor. The average current in the inductor is determined by recognizing that the average power supplied by the source must be the same as average power absorbed by the load. So we have Pin equals to Pout. Then we know Vin In equals to Vout Iout. And our In is our current on inductor. So then we have our average inductor current is Vin divided on 1 minus 2 square times R. The maximum and minimum inductor current are also determined by using the average value and the changing in current. And also the CCM and DCM boundary is divided by IL minimum is 0. The peak-to-peak output voltage ripple can be calculated from the capacitor current waveform. The current waveform on a capacitor is minus Vout when the switch is on, and when the switch is off, it's the inductor current minus the output current. The charge in capacitor charge can be calculated from delta Q equals to C delta V out. And the area on the inductor current is I out times dt, and the charge on capacitor is equal, so that we get the voltage ripple and capacitance relationship, which is C times delta V out equals to V out divided on R times dt. Again, for the question in the tutorial, you can download the solution on Canvas. You can follow it step by step. I'll only give you some summaries to help you solve more questions about boost converter. Same with buck converter, we have examine questions and design questions. The typical examine question is like the question in your tutorial 617, and the design question is 619. So we actually use the same equation but play differently. For examine question, we usually ask to calculate the current ripple and voltage ripple. So our target is to find the delta IL and delta V out. For the design questions, we are asked to calculate the inductance and capacitance for the ripple they provide to us. A little bit hint here, in question 619, it doesn't give you the exact current ripple they asked. They just said it's 50% of average inductance current, so you need to have the average inductor current first. I put all the equation I thought you are going to use in the tutorial for the boost converter. Go play with them first. If you have any question, welcome to our Q&A session on Zoom. A little bit hint here. In question 618, it asks us to calculate the RMS value of capacitor current. Because the waveform is not square wave or triangle wave we learned in our first tutorial, so you need to use the RMS definition equation. I'll leave the RMS definition equation here.